guys. I'll go ahead and record this for people that aren't joining us today. So this is the free response from Unit 4. I emailed you guys back all of your responses, and you should see on each section either an E, a P, or an I. Remember that E stands for essentially correct, a P is partially correct, and then an I is incorrect. So if you check your email and want to pull up your own test to kind of see where you might have had issues. Overall, we did really well with question 9. That was the best of the 3. We did pretty well on question 10, and then we had some major problems on question 11. Specifically down here with the standard deviation. So if you were to look at your scores on these 3 problems, that's generally what happened. The highest scores were on question 9, and then they went down a little on question 10, and then they went really down on question 11. But I'm not surprised. Question 11 was hard. Let's see. So question 9 says, a simple random sample of adults living in a mid-sized city were selected. Age and annual income for each adult in the sample were recorded. The resulting data is summarized in this table. A, what is the probability that a person chosen at random from this sample will be in the 46 to 60 age group? So there's the 46 to 60 age group. There is the number of people in the sample, 49, that are in that age group out of 206. So this was literally dividing. So 49 divided by 206. There are 49 people divided by 206. And this was either you got it or you didn't. So it was either scored as essentially correct if you got that, or incorrect if you did not. So on this particular question, they did not allow for any partial credit, because I mean, literally that's all you had to do was just divide those 2 numbers, okay? On part B, however, this is now a conditional probability. So the conditional probability says, what's the probability that a person chosen at random from those in the sample whose incomes are between 35 and 50,000. So now we're just looking at those people right there. So ignore everybody else. Just looking at those people, what's the probability that someone chosen at random from those people will be 46 to 60? So 46 to 60 out of this group, there are 15 out of 68. So if I divide that, by the way, you could leave it as a fraction, but the reason I'm dividing it is because it'll be useful in part C if we have some decimal answers here. Okay, so that was part B. They actually did allow for partial credit on part B, like if you used the wrong group, like if you used this group instead or that group instead, so you misinterpreted, and grabbed the wrong condition here. So they did allow for some partial credit, but not a whole lot, because there's not really a whole lot of things you can do wrong that are still partially correct there. So taking that group and then dividing the same way that we did in part A. Okay, part C, based on your answers. Now this is important. You got to base it off of these answers, not on some other reasoning whatsoever. Based on those answers, is annual income independent of age category? Okay. Now this here is the probability of everybody being in this age group. Okay, so I could call this, for example, the probability of A being in that age group. This is the probability of being in that age group given that you have this salary. So this is basically the probability of being in the same age group given that you have a salary. Okay. Remember, independence means that these 2 have to be the same. Are these 2 the same? No, they are not. So they are not independent. And that's really all you had to say here, is because my answer to part A and part B are not equal. Therefore, annual income is not independent of age in this sample. Okay, might be different for a different sample. They're close. So maybe in the entire population, they're independent, but in this particular sample, these are not the same. So that's really all you needed to say for C. I'm not going to write that out because I think you guys get that. They are not independent because these are not equal. Independence means that these two probabilities have to be equal. So they are not independent because those are not equal. Okay, number 10. A certain airline says that frequent flyers that normally fly coach can get upgraded to first class on any randomly selected flight, if you're lucky, 15% of the time. So if you are a frequent flyer, you have a 15% chance of getting upgraded. Of course, I'm not a frequent flyer, so this wouldn't apply to me anyway. Okay, so the upgrade probability is 0.15. This outcome is independent for all flights. Jeremy flies this airline frequently, so he is a frequent flyer, and he always purchases coach tickets. So what's the probability that Jeremy's first upgrade occurs sometime after his fourth flight? So in other words, what's the probability he gets an upgrade, not on the first or second or third or the fourth, but sometime after that, maybe on the 5th or the 6th or the 7th or the 8th or the 9th or, et cetera. Okay? Now, there's actually two ways to do this. So one way would be to think of this as geometric. And we are looking for the probability that he gets upgraded sometime after the fourth flight. So the probability of an upgrade at any time is 0.15. X would be the number of flights until the upgrade. So using a geometric distribution, we are looking for the probability that X happens, the upgrade happens, after the fourth flight. So we can do this as geometric. What's the probability that you get upgraded after the fourth flight? Now, if you're going to do geometric CDF on your calculator, which you probably would do this if you're going to use geometric distribution on this, calculator does not do greater than, but calculator does do less than or equal to. The opposite of greater than 4, the complement is less than or equal to 4. So I can go to geometric PDF, or excuse me, CDF, with that as my P. There's no N in geometric, and I can do 1 minus. So I go to second distribution, geometric CDF, find it right there, and put in 0.15, and my X value is 4. Paste that in there, and then I do 1 minus that value, and I get my answer. So this is 1 minus 0.4779, and I get 0.522. Okay, so that's one way to do it. Okay, it is geometric because we're just, how long does it take until you get your first upgrade? But another way to think about it is, well, if you get your first upgrade after the fourth flight, then that means what's the probability? You do not get upgraded on the first or the second or the third or the fourth. So you could take the opposite of this and say, well, no upgrades for the first 4 flights. So you could say, I don't want to be upgraded at all. Well, not want to be upgraded, but suppose you don't get upgraded at all on the first 4 flights. That means that your upgrade has to happen after the first 4 flights. Notice you get the same answer. So that's okay too. So whichever way you did that, I had people do it both ways. So you can interpret it this way. If your upgrade happens after the 4th flight, that means the first 4 flights, there's no upgrades. So you're really finding the probability of not getting upgraded 4 times in a row for your first 4 flights, or using a geometric distribution with greater than 4. Okay, part B. What's the probability he gets upgraded exactly 3 times in his next 12 flights? Now we have a value of N. He's going to take 12 flights. X is going to be the number of upgrades. And we want him to get exactly 3 upgrades. This is no longer geometric. What is this? Parts of the B. Binomial. So I can do this on my calculator, and as long as I say it's binomial, there's my n, there's my p, there's my x, everything is labeled here. Some of you guys did not label. You do not get full credit without labeling, but that's what I would do. Binomial PDF 12.5, my x is 3, and we get 0.1720. Yep. Part C, Jeremy will take 85 flights during the next 6 months. Would you be surprised if he gets upgraded to first class more than 20 times? So this is also binomial, if you want to do it this way. So n would now be 85, p is still 0.15, and x is the number of upgrades, same as the last one. Upgrades. We want to know what's the probability that he gets upgraded more than 20 times. So is that going to be surprising? Calculator does not do greater than, but we can do less than or equal to 20. That is the opposite of greater than 20. More than 20, 20 or less. So I can do this on my calculator with binomial CDF with those values right there. So binomial CDF, remember CDF does less than or equal to, PDF just does equal to. So 85.15, 20. One minus. Okay, so that's his chances of getting upgraded more than 20 times. So if it happened, would you be surprised? Yeah, it's a small percent. So it should only happen about a 1% chance of it happening. So yeah, when something that only is supposed to happen 1% of the time happens, yeah, it's surprising. So the answer to this is yes, we're most likely going to be surprised because it should only happen 1% of the time. Another option is you could use a normal model here, okay? If you use a normal model, you have to check that a normal model applies. So you got to show that NP is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. I'm not going to go through all of this, but there were a couple that used a normal model and one person that did not explain why it's appropriate. So this is what you have to do to explain that it's appropriate. Show that those are both greater than 10. I can now use a normal model. My mean is going to be NP, that's the mean for binomial, and the standard deviation would be the square root of n times p times 1 minus p. So if you verify the normal model, yes, you can use a normal model on this. Because remember, that's one of the things that we learned is that a normal model can approximate a binomial model as long as NP and n times 1 minus p are each 10, which we have been now using all the time with sample proportions. Okay, our last one. A set of drinking glasses is packaged into a box. The full box consists of 8 randomly selected glasses and 1 randomly selected empty box. So we have 8 glasses and 1 box. The weights of a full box, so that's 1 box plus 8 glasses, is approximately normally distributed with a mean of 9.97 pounds and a standard deviation of 0.56 pounds. What's the probability that a randomly selected full box will weigh more than 11 pounds? Now it says that the full box is normally distributed with a mean of 9.97. 11 is over here somewhere. So it is asking for that probability off of a normal model. So using this normal model with a mean of 9.97 and a standard deviation of 0.56. And this is my lower is 11. My upper would just be some really large number. And this is normal CDF. So that's probably the easiest way to do that. So the probability of a full box, I'll just call it X, being more than 11 is second distribution, normal CDF, 11, big number. Mean is 9.97. Standard deviation 0.56. 0.0329. Okay, about a 3% chance of a randomly selected full box weighing more than 11 pounds, because it's supposed to average just at about 10 pounds, but there's variability in the weight of each of the glasses and in the box itself. Okay, part B. The weights of the empty boxes have a mean of 2.23 pounds. That's how much the box empty weighs, with a standard deviation of 0.13. It is reasonable to assume that the weights of the glasses and the weights of the boxes are independent. It's also reasonable to assume that the weights of the randomly chosen glasses are independent from each other. So everything's independent. Okay, let random variable X be the weight of one drinking glass. Okay, so what do we have here? We have 8 drinking glasses plus 1 box. And that's what we're looking at. 8 drinking glasses plus 1 box. What's the mean of X? Means work exactly like this. In other words, 8 times the mean of X plus the mean of the box should equal the full box. Okay, the full box is 9.97. I don't know what this value is, but I do know that the box averages 2.28. So basically we have this. 2.23, excuse me. So I'm just going to solve this. In other words, I'm going to subtract here and divide by 8. So if we do that, 9.97 minus 2.23, and then divide that by 8. The mean of a glass is 0.9675 pounds. Okay, I just got that from solving. Okay, so each glass has an average. There's 8 of them. And the box has an average weight of 2.23. The total box together has an average weight of 9.97. So means you can work with them just like you do with the individual values. Standard deviations. Can we add standard deviations like I added these means here? No. So this is the hardest one because of the standard deviation, but you could still get a 3 on this if you made a reasonable attempt here. But what we do know is no, you can't add standard deviations. So I've got my first glass. It has a standard deviation of, that's what we don't know. We're trying to find the standard deviation of X. So we have an individual glass. It has a standard deviation that I do not know, but I know that I can square it. That's my variance. I've got a second glass, has the same standard deviation. I'm going to add that in there, but I can't because it's standard deviation, so I'm going to square it. So I'm going to do the variance. This is the variance of one glass. There are 8 glasses. So there's 8 variances. Plus, I can add the variance of the box. The box has a standard deviation of 0.13. So I am not adding standard deviations, I'm adding variances. That's the variance of one glass. There are 8 of them. Plus, that's the variance of the empty box. And the variance of the full box with 8 glasses in it is 0.56 squared. That's the equation that we need to solve. So we now need to solve for this. So what am I going to do? I'm going to subtract here. I'm going to divide by 8, and then I have to take the square root. Okay, so that's the equation that we are going to solve. So 8 times the standard deviation of X squared is equal to, if I square that and subtract that, 0.56 squared minus 0.13 squared. And some people look at that and say, wait a minute, we just subtracted variances. Well, yeah, we subtracted these 2 variances, but not because we were combining them, but because we were solving an equation. So yeah, in solving this equation, I do end up subtracting these variances, but it's because I'm adding these variances together. That's the total there. So I get that, divide by 8. If I divide that by 8, I get 0.03708. And then my last step would be to take the square root. Which is about 0.1926. Okay. So yes, that one was hard. This was based off of a live AP question, and it was hard when it was live for the students who took the AP exam. Okay. But like I said, you could still get a 3 on this if you made a reasonable attempt showing that you knew you're supposed to add the variances here. And the mean, you just do that to get the mean. 8 glasses plus a box equals the mean of the full box. And then this was just a normal model. Okay, so we have a whole bunch of stuff for you guys to work on. There is a worksheet on inference for proportions. You guys have 2 progress checks on AP Classroom, so that's just some multiple choice questions on proportions. You've got a book assignment, you've got a reading guide, so you've got the rest of class today, which is about 50 minutes plus, the rest of the day, weekend, all of that. Before you guys do that, I want to give you some quick notes here. Inference. Okay. So we're doing inference specifically for proportions. Inference is 2 things. One thing that you might be asked on inference is you might be asked to do a confidence interval. Okay? When you are asked to do a confidence interval, do not forget to panic. In other words, I'm going to give you a little acronym of what you need to include in a confidence interval problem. So when you see a confidence interval, you need to panic. What do you need? You need to define your parameter. Okay. For example, let P equal the proportion of whatever. So what is it you're trying to estimate? So let P equal the proportion of M&Ms that are yellow. Okay. A, you need to check your assumptions and conditions. Specifically, we need a random sample. We need the sample to be less than 10% of the population, and we need n times p and n times 1 minus p to be at least 10. On your worksheet today, there's at least one problem where the conditions are not met, so you may stop at that point. If the conditions are not met, you do not have to continue. On the AP exam, all conditions will be met, unless they are asking you specifically, hey, here's the situation. Are the conditions met? Explain why or why not. Then yeah, it's possible they're not met. But if they ask you to create a confidence interval, yeah, the conditions are going to be met. They're not going to ask you to do something that you shouldn't. So they're not going to say, hey, create a confidence interval. Trick question. Really, you shouldn't create a confidence interval because our conditions aren't met. So you just need to be able to verify the conditions on an exam. Okay. N, you need to name the interval or provide the formula. Whoops, formula. So in other words, write the formula down for the interval or name the interval. If you're going to name the interval, that means you're going to do this on your calculator. So you need to write that you are doing a 1 proportion Z interval. So if you choose to do this on your calculator, which is my recommendation, less room for error, just write down, this is a 1 proportion Z interval. You need to write down the interval. Your interval should be written like this. 2 numbers in parentheses, a lower value and an upper value. So your interval is going to have a lower value here and an upper value here. Okay? And if you do it on your calculator, that's fine, as long as you have named which interval you are using. If you're going to use the formula, then obviously anybody reading it will know which interval you're using because of the formula you used. And then numbers, or C, you need to interpret in context. That's what the C is for. So define your parameter, P. Check your assumptions, A. Name your interval, provide your interval, interpret in context. How do you interpret? I am whatever % confident that the interval from A to B has captured the true proportion of M&Ms that are yellow, or whatever it is, okay? So you guys know how to write your conclusion or your interpretation, okay? So if you are going to do a confidence interval problem, that's all that you should include in your answer. If you are going to do a hypothesis test, also called a significance test, also called a statistical test, also called testing a claim. Lots of different ways to refer to this. Don't forget phantoms. There is more involved here. So our acronym for a hypothesis test is phantoms. First thing, define your parameter. Right, so just like with the confidence interval, let P equal, the proportion of whatever. H, write hypotheses. You need a null hypothesis. And you need an alternative hypothesis. The alternative will either be greater than, less than, or not equal to. So H4, write down your hypotheses. You need 2 of them. A, same as up there. Check your assumptions and conditions. Same ones. N, same as up there. Name the test or show all of your work. I recommend naming the test. It's called a one proportion z-test. Since all of my conditions are met, I am going to do a one proportion z-test. Sampling distribution is based off of a normal model. Okay. T, you need to provide a test statistic. That's a z-score. And a p-value. If you do it on the calculator, it gives it to you. You just write it down. Okay, how come I don't remember what O is? Phantoms. I think that's where the p-value goes. I think this was observe your p-value. P-value compared to alpha. Alpha, usually 5%. So observe how your p-value compares to alpha. M, make a decision. Okay, your decision, you reject the null when your p-value is low. Your p-value is not low, you fail to reject the null, okay? And you need to explain why. You need to explain how you observe your p-value to be low or not low. And then the last thing is you need to state a conclusion in context. So all of these last three are really your conclusion. So since my p-value of 0.03 is less than 5%, I reject the null hypothesis. My conclusion is there is sufficient evidence to say that the true proportion of M&Ms that are yellow is less than 20%. That would be an example of a full conclusion, but it involves all three of these things. So you need to look at your p-value and tell me, how does it compare to the 5% significance level? Based on that, make a decision, fail to reject or reject the null. And then what does that mean in the context of the problem? Okay, so as you are doing problems, if it asks you to do a confidence interval, it's really obvious when it asks you to do a confidence interval. It will say, create a 95% confidence interval. There is no way that they can expect you to do a confidence interval unless they blatantly ask for one. So any problem that says create a 95% confidence interval, you know that you're doing a confidence interval, and that's where you're going to panic. Here, if they want you to do this, they will say test a claim, test this hypothesis at the 5% significance level, or is there evidence that something is true? So those kind of wordings are going to tell you to do a test. The most common one is is there enough evidence to say that this is true? So a hypothesis test is literally testing your evidence to see whether it is strong enough to make a conclusion. Okay, so I'll leave that up there and you guys can think of those hopefully to make sure that you include all the parts. Okay, so question on the chat says, will it be assigned unit 5, multiple choice parts B and C? No. We will be doing, the question was on the personal progress checks. We did 5A earlier, but if you look at the progress checks for today, it's 5 or 6, A and B. So yeah, we did skip some, but there is a reason for that because the order that the AP exam College Board puts those out doesn't exactly follow the order of what we've covered. So we will go back to those. We just can't do those yet because there's some information for those that we have not covered that we will get to when we do chapter 21. So for now, just do the ones that I ask you to do, which is 6A and B, which is on confidence intervals and tests. Okay, so right now, like I said, we've got plenty of time, like 45 minutes, work on the worksheet that's in there. It's basically just more samples of these. You've got the book assignment, you've got a reading guide, you've got some progress checks. So use the next 45 minutes. I'm going to walk around with the students that are here in class. If you're online and you need me, I'm going to put my camera on. So I'm going to pause the